Good morning, I am Irshad Siddiqui. Today I am going to discuss chemistry of 12th class and the topic is solid state. Subtopic is unit cell in 2D and 3D, that is two-dimensional and three-dimensional. In two-dimensional, lattice, the unit cell is an area. It means it contains length and width. Simplest crystal structure in 2D can be represented as, this is the simplest crystal structure in two-dimensional. This is known as crystal lattice in two-dimensional. The simplest part is known as unit cell. Unit cell. So, in two-dimensional, there are following types of unit cells, that is oblique unit cell, square unit cell, centered rectangular unit cell, primitive rectangular unit cell, and last one is hexagonal unit cell. So in two-dimensional there are 5 types of unit cell which I am going to discuss one by one. Unit cell is characterized by edge length, that is A, B, and angle between the edges, that is gamma. In oblique unit cell, A is not equal to V and gamma is not equal to 90 degree. So this is A and this is B. A is not equal to V and gamma is not equal to 90 degree. And we can represent lattice point at the corner. Okay, so there are 4 lattice points. So in oblique unit cell, A is not equal to B and gamma is not equal to 90 degree. Next one is square unit cell. In square unit cell, A is equal to B and gamma is equal to 90 degree. Angle between the edges, that is A and B, is 90 degree. So A is equal to B and gamma is equal to 90 degree. So in square unit cell, edges are same and angle between the edges is 90 degree. Next one is centered rectangular unit cell. Next one is centered rectangular unit cell. Centered rectangular unit cell. Centered rectangular unit cell. Okay, in center rectangular unit cell, A is not equal to B. A is not equal to B, but gamma is equal to 90 degree. So center rectangular unit cell can be represented as, in this way, and center there is a lattice point. A is not equal to B and gamma is equal to 90 degree. So in center rectangular unit cell, A is not equal to B but gamma is equal to 90 degree, and the lattice points present corner as well as center of unit cell. So in centered rectangular unit cell, A is not equal to B but gamma is equal to 90 degree. Lattice points are, this is the lattice point, and lattice point, and center is also contain a lattice point. Next one is primitive rectangular unit cell. Fourth one is primitive rectangular unit cell. Fourth is primitive rectangular unit cell. In primitive rectangular unit cell, A is not equal to B but gamma is equal to 90 degree. Okay, A is not equal to B but gamma is equal to 90 degree. So the lattice point are, this is A and this is B. So in primitive rectangular unit cell, A is not equal to B but gamma is equal to 90 degree. There is no lattice point at the center. Okay, and last one is hexagonal. Last one is hexagonal unit cell. Fifth one is hexagonal unit cell. In hexagonal unit cell, A is equal to B and gamma is equal to 120 degree. So this is B and this is A. So the angle gamma is equal to 120 degree, A is equal to B. Okay. So in hexagonal unit cell, gamma is equal to 120 degree and A is equal to B. So in this way we can explain in two-dimensional lattice there are 5 types of unit cell. First one is oblique unit cell, second one is square unit cell, and third one is centered rectangular unit cell, and fourth one is primitive rectangular unit cell, and last one is hexagonal unit cell. Okay, in three-dimensional lattice the unit cell is volume. It means it contains length, width and height. Okay, how we can represent three-dimensional lattice? We can easily represent three-dimensional lattice in this way. We can explain three-dimensional lattice each point contain the line cut contain a lattice point. This is the lattice point, and this is the lattice point. So this is three-dimensional lattice. So this is the three-dimensional lattice. So in this way we can represent the three-dimensional lattice. How many types of unit cell in three-dimensional lattice? There are 2 types of unit cell in three-dimensional lattice. There are 2 types of unit cell in three-dimensional lattice. Unit cell in three-dimensional lattice, that is primitive unit cell, and centered unit cell. In primitive unit cell, the lattice point present at the corner only. Lattice point present at the corner. Lattice point present at the corner. 1, 2, 3, 4, 5, 6, 7, 8. A is equal to B is equal to C. This is the length, this is the width, and this is the height. So in primitive unit cell, A is equal to B is equal to C, and gamma is equal to 90 degree, and lattice point present at the corner. Centered unit cell, that is, there are following type of face centered, body centered, and end centered. So in three-dimensional lattice, the unit cell are primitive unit cell, and second one is centered unit cell. Centered unit cell are face centered, body centered, and end centered, which I have already discussed how to calculate the number of atom in a unit cell. Next topic is packing in solid. Packing in solid, that is closed packed structure. Closed packed structure. Constant in solid, constituent particles are considered as hard sphere. Just like in this way, they are considered as a hard sphere and leaving a minimum vacant space, which is known as voids. In solid, the constituent particles considered as a hard sphere and leaving a minimum vacant space, which is known as voids. So, in solid, close packing in one dimension, close packing in two dimension, and close packing in three dimension. So first of all, I am going to discuss close packing in one dimension. Close packing in one dimension. In one dimension, constant particles packed in this way. Constant particles are packed in this way. In one dimension, constant particles are packed in this way. So the coordination number of in this type of packing is 2, because one hard sphere is surrounded by attached with two adjacent atoms. This it attaches with this atom and this is attached with this atom. So the coordination number is equal to 2, because each sphere is surrounded with two atom or two hard sphere. So the coordination number is equal to 2. In two dimension close packing, second one is two-dimensional close packing. I will discuss in next video for two-dimensional close packing. Thank you for watching the video.